Good afternoon, everybody, and welcome to my presentation, which has been called Picking Up Good Vibrations, a Good Link to Good Music, Exploration of the Intensified Vibratory Mill via a Modern Design of Experiments approach. As most people attending this session work in a pharmaceutical laboratory, often in a pharmaceutical company, you all know that if the company finds this new chemical entity with high potency, meaning that it works really well on a disease, it can cure the disease, perhaps it can save life, it's a brilliant day for that pharmaceutical company. But what do we often find? This poor aqueous solubility and or low dissolution rate, meaning that although this new chemical entity works really well, it has this really low oral bioavailability. Of course, we want to increase this poor aqueous solubility. We want to enhance that dissolution rate to increase that bioavailability and therefore to make our patients happy again. And what do we do to really increase these properties? Well, the company often comes to our laboratory of the formulation scientists, and this is probably nothing new for you, the different strategies that you can apply to increase the pore aqueous solubility and or the dissolution rate, such as cyclodextrins, amorphous salt dispersions, nano and micro suspensions, but also many others. But our focus today will be on the nano and micro suspensions. Nano and micro suspensions can be produced in two ways, the bottom-up approaches and the top-down technologies. And if we now focus on these top-down technologies, you find that it's subdivided into really big categories. On the one hand, you had wet milling technologies, and really the star player in this category is wet bead milling. And the second big category is high pressure homogenization technology, which is then further subdivided in the piston gap homogenization methods and microfluidization methods. So over these two big categories, there's actually one golden standard, one star player, and that is wet bead milling. And it's quite clear why it has these golden position, why it still contains that golden position due to its many advantages. It's easy to scale up, commercial viable, so it means that already a lot of products on the market are formulated, are produced with this technology, it's cost effective, etc. Though it has some disadvantages as well. It has a cumbersome drug product development, so a lot of trial and error is still needed to really find that final formulation, and it has this long milling time which can uptake hours up until days. And of course, we want to improve, we want to advance, so we start to get thinking about getting rid of these advantages and finding a new technology, such as intensified vibratory milling, which is a new technology really underexplored and only on the market for a couple of years. So this is the intensified vibratory mill, and my best friend has to say for the past 4 years. And what do? Well, we put our recipients, as you see over here, and the recipient in our case was a vial filled with API zirconia beads and media. And what happens? So again, we place a recipient over here, and below the recipient over here, you have this spring damper system. So it's a spring damper system, meaning that the springs will elongate and reduce over time, and therefore giving this vibratory motion that is then reflected to the recipient, as we can see over here. So the recipient starts move up and down, and starts to vibrate. But what happens then? Well, if we would fill the vial again with the green beads are the API, and let's imagine that the blue beads are the zirconia beads. If you see the progress over time, well, everything goes crazy, everything starts to jump around, and at the end, there is a lot of grinding that can appear. So you can have ball impact, pressure, shear, etc. And in the end, the particle size of the API will reduce, and hopefully, of course, up until the nano and micro level to produce those nano and micro suspensions. So the IVM on itself is a mixing system, but by adding these beads, the addition of beads, we can have a milling system. The basis of this milling system is that vertical displacement of that spring damper system. And if you, of course, would follow this motion over time, you will end up with a sinusoidal wave. A sinusoidal wave, as seen over here, has two really important characteristics. The period or frequency, which is here set, fixed at a value of 60 Hertz, and an amplitude, which you can see over here. And amplitude is really how high that vertical displacement is, how high and how low will it go, and you can change that. You can alter it, and it's reflected in the acceleration. So the acceleration is of course a value of this vertical displacement and gives an idea of how much energy has been input in the system. So the process parameters that you can alter of the intensified vibratory mill is first hand your content of your recipient. So you can change the bead suspension ratio, how many beads will you add, the bead size, will we use big beads, small beads, etc. And also we can also change how we mill. Will we mill for a long time? That acceleration, how high and low will we go in that vibratory motion, etc. So these are some examples. So it's quite an extensive list, and they do have one and the same thing in common. They all have an important impact on that final particle size. And of course, we want to obtain nano and micro suspensions, then it's really important to have a good final particle size, really in that nano and micro range, of course. But if we then go to the laboratory, we saw that all these parameters were really optimized via a trial and error approach, or maybe often a one variable at a time approach. So of course we lose a lot of money, a lot of time, a lot of effort in the laboratory with finding this optimal process parameters to really find a nano suspension, to really find a micro suspensions. And of course, keeping in mind that we still have this new chemical entity, we want to get these drugs as fast as possible on the market, as we of course want to cure patients as fast as possible. Therefore, if we want to get rid of these trial and error approaches, if we really want to get this better insight in these new technologies, and in the best case, if we want to predict production outcomes, we have to find a new approach. And of course, therefore, we will use a design of experiments. So, as an input of the DOE that we applied, that we created, it was this. So the factors that we have chosen for DOE was the acceleration. So again, that amplitude that you set for the sinusoidal wave, the bead size, the bead suspension ratio. So how many beads versus suspension will you add in your vial? The milling time, how long will we mill? And the breaks during milling. This means that you insert a pause where the system is at rest so that it doesn't move at all. So if we would visualize that a bit, this would be our design space. So at the x-axis below, you can see the acceleration, so 50 up until 80 G. Breaks during milling, 0 minutes, so a continuous milling up until 5 minutes that we pause. Bead suspension ratio, 0.375 up until 1.2. And milling time, 10 to 30 minutes. So really a fast milling. After 30 minutes, we would like to achieve a nano or microparticle. And then the size of the dots actually represent the bead size. So the small dots are the smallest beads that we used. The big dots are the biggest beads that we used. And hopefully you can appreciate with every dot representing an experiment that the design space is really well covered. So the responses that we're going to investigate is the temperature after milling. Because of the fact that we saw in early experiments that IVN probably really can produce nano and micro suspensions, but that the vials became so hot, really hot, hot, hot. And of course, we want to reduce that temperature that is generated. Other responses, of course, are the particle size distribution, which is then characterized by the DV50 value, DV90 value found with LD and confirmed with SEM, and also the span to have an idea of the width of the particle size distribution. The parameters that we investigated were all the main effects, all quadratic effects, all two-way interactions, and even one three-way interaction, which is normally omitted out of a DOE, but we have chosen really specifically to edit. And this three-way interaction was acceleration, bead suspension ratio, and bead size. So really 22 parameters in total. So quite broad investigation. So if we then look to the power that we applied, is that we set a really high power for main effects. We really want to see if they are statistical significant. We chose to have a medium power for two-way interactions. Of course, we were limited to 30 experiments, so the power for the quadratic effects were rather low, but of course we still want to see what happens. And we still have our three-way interaction with as well a moderate power to really see if it's statistical significance. So what was the output of the DOE? Of course, it is a very broad analysis that we did, but we want to give you some key conclusions that we made. So first of all, I want to raise a question. How many parameters do you think that were significant for temperature, statistically significant? So I just give you 1 second to think. What do you expect if you have 22 parameters with only 5 main effects? So meaning that 17 parameters really imply a quite complex system with two-way interactions, a three-way interaction, quadratic effects, etc. So do you expect 1, 2, 3, 5, or do you expect 20? What would you think? Well, the numbers will blow your mind. Because, for example, for temperature, we found that 15 of the 22 parameters were already statistically significant. So if we look at the left-hand side, you see all these investigated parameters, the main effect, the two-way interactions, quadratic interaction, and three-way interaction. And let's see to this fifth column, and every time that this value is colored in orange or red, it means that it has the statistical significance, and it's quite clear that this broad set of parameters were statistically significant. So having an effect on the temperature. What you can already also see in this table is that all main effects had an effect, but also a lot of two-way interactions. Even here, a quadratic effect of bead size, even though we said that there was this quite low power. So it's really indicating the complexity of this milling system. Keeping in mind that for some variables there was a low power, so even if there was perhaps a bigger sample size, we could have seen even more. But okay, it's really complex. There is a lot of data, of course, but what can we do with it? Yeah, it actually the possibilities and opportunities are broad, immense. We can conclude things with it, we can explain, we can optimize, we can predict, we can do it all. So to give you an idea, an example of some of these verbs, as to say, first of all, we can explain things with it. So with this DOE, we've proven the existence of the optimal bead size. Sometimes they say, just take the smallest bead. It's always the best. Well, it isn't. And how did we prove this with this DOE? First of all, via that three-way interaction, which was significant for the DV50 value, which means that depending on your acceleration, for example, if you alter the acceleration, this will have an effect on how the bead size versus bead suspension ratio, that two-way interaction alter. So it really shows the complexity and that these two variables, acceleration and bead suspension ratio, will have an input, an influence on which bead size is actually optimal. To really give it to you in an example, here we have a situation with a low energy with 50 G. And what you can see here is the DV50 value really gets smaller if we use a big bead. Whereas in a high energy status, the ATG, the smallest bead size seem more favorable. And how can we explain that? So if we then look to the bead size, of course, the biggest beads weigh more. And if we then look to the equation of kinetic energy, we see that an increase in mass means that there is also an increase in kinetic energy, meaning that this biggest bead will generate more energy to your system and of course will increase the particle size reduction. Though, if we then take a few beads together, you can already see that the voids in between the beads will be bigger for the biggest bead, so that actually a bigger particle can evade the comminution, the milling, during by placing itself in between this void. In this way, it's quite clear that for the mass, you would say take the biggest bead, but for evading the voids, take the smallest beads. So it's really finding that balance. So secondly, we can of course predict outcomes as well. So if we look back to this enormous data set of temperature, just giving one example, and again, the broad set of parameters that were significant, well, we decided to include everything, so all parameters in a final prediction expression, because of the fact that, again, the power, if it was increased, perhaps they were significant as well. So the final prediction expression would be this. It's quite an extensive equation, as you can see. Luckily, the jump software that we use can fill it in ourselves, but here you should fill in acceleration, brakes during milling, etc. And with including this, filling it in, you can predict what the temperature would be in the laboratory. What did we saw? Well, it was really good. So for example, here you can see the predicted temperatures, and here in the y-axis you can see the what we found in the laboratory, and it really fits really well. With a determination coefficient of 0.99, we really cannot be unhappy about it, as to say. So of course, applying these prediction expressions on temperature, but also on the DV50 value and span, we really can reduce our lab work, just simulate your results, predict your results beforehand, and not have to go to the laboratory. And we can, of course, reduce time, money, effort, etc. Already showing the strength of applying these DOEs. We can also predict via simulations. To give you an example, we set here the specification limits of, for example, we want a DV50 value below 5 micrometer, and we want to have a temperature that will not get higher than 50 degrees. And then you fill these specification limits in your software, and it will just run and simulate some random results, some random experiments in a laboratory. So these would be the process parameters then, and these were the simulated DV50 values and temperatures, so predicted by the software based on these prediction expressions. Of course, it gives an extensive list, and we have chosen these 5 settings. Then we converted these settings to values that we can use, that we can apply in the laboratory because, for example, an acceleration of 59 can be set, but not 58 points, etc., etc. And their forecasted output. So we filled this in again in the software, and this was forecasted again. So if we then went to the library, really performed the experiments, these were the results. So if we have for 5 samples, these were the predicted temperatures, and this was what we measured in the laboratory. And for here, we have the predicted TV50 values and the measured TV50 values. We can already see that the simulated results are a bit higher than what we got in the laboratory. The variability of the measurements can be a reason, but still quite interesting that we can get pretty close to what we predicted, and it can already be a rule of thumb of what we're going to do in the laboratory, and therefore reducing our laboratory work. So with this presentation, I already wanted to show you the strength of the modern DOE and also a deep dive in IBM. Of course, the time was short, and therefore I would like to refer to the publication that we've written if you need more details. And of course, thank you for following, but I will be hanging you around for your questions. Thank you.